All right, guys. So from today, we will start the much dreaded dynamic programming, and we will build on the difficulty. So I'll tell you the agenda for today. So as I said, we want to start dynamic programming today. Today, basically, we will look at 1D subproblems. So these are basically 1D subproblems which can be solved in order n time. And we will, if time permits, we will look at 1D subproblem which can be solved in order n square time. So that's basically the agenda for today. Most of this we hope to cover, and some parts of this is what we will be covering by the end of this lecture. No, Rishabh, this is not the last topic. You have graphs also, right? After this, so you can check the timeline for that. I guess the timeline has the details. Okay, so let's start. So what do you understand by dynamic programming? That's the first thing that I want you to know. Or so what is your idea when you hear the word dynamic programming? Can I have some answers?
Dynamic programming basically means breaking down the bigger problem into smaller subproblems, like we did in recursion. And what happens in recursion is that we tend to, sometimes in some questions, we tend to frequent a particular subproblem many times. So the computations get repeated. So in dynamic programming, we store those values for those particular subproblems. And if we ever encounter them again, then we can just return the value in O1 using some memory.
Yes. So I think Ritik pretty much summarized everything that we understand. So dynamic programming, first of all, it underneath it uses the divide and conquer paradigm. So just try and understand what basically happens is you have a bigger problem. Like I have told this many number of times, but I'll again repeat this. So you have a bigger problem that you want to solve, and what you do is instead you focus on solving sub problems. So sub problems are smaller instances of the same problem, and you combine these sub problems to obtain a solution for the bigger problem. So this is basically the paradigm that we use to solve a problem. You say that you have a bigger problem. What you do is you divide it into smaller problems. You solve these smaller problems, and you use them, you combine them to solve the bigger problem. So that's basically the paradigm that we use. And this is very similar to some problems that we looked at in recursion. The only difference here is that here you will see the same sub problem repeating again and again. So when you are solving a bigger problem, what happens is let's say you are solving two problems, P1 and P2. What happens is when you are solving P1, you will solve it by solving a smaller problem, a problem Pi, which is less than P1. Here also you will solve, for solving P2, you will solve a problem, let's say Pj, which is smaller than P2. So in dynamic programming, what happens is when you solve the smaller problem, it will happen that the smaller problems come out to be the same for different bigger subproblems. And that's when we say that when we are solving a smaller problem again, we don't need to do that again. Instead, what we can do is we can reuse the solution that we obtained when we were solving P1. And that's basically the idea of dynamic programming. So we will see all the essentials of dynamic programming. Let's take an example to illustrate that better. Let's take this example. And this is question number 198. Let's start with this question. And I will illustrate to you all the essentials of dynamic programming through this example. So go through this question. So I will just tell you what the question is telling you. The question is telling you that you have houses which are lined up one after the other, and you are given an array of numbers where AI basically denotes the amount of money you can rob from the ith house. So you could have numbers like 32, 46, 60, 16, and let's say 12. So from the 0th house, you can obtain a maximum of 32 rupees or 32 units of money. From the first house, you can obtain 46. So these are the houses that are lined one after the other, and this is the amount of money that is present in each of the houses. Now you have a robber who wishes to rob one or more houses from this society, and the only constraint is that if he robs a particular house, the ith house, he cannot rob the adjacent houses which are adjacent to I. That's the only constraint that you have, and you have to determine the total number of the total amount of money, that the maximum amount of money that the robber can get from the houses. Is the question clear to everyone? I will explain all the essentials of what's going on through this question. We will take this as a running example, but is the question, the problem statement clear to everyone? Yeah, quickly. Okay. So now let's see. So what is my thought process when I get this question? Broadly, using dynamic programming, there are two types of problems that you can solve: the optimization problems and combinatorial problems. So these are broadly the two types of problems that can be solved. Optimization problems are problems wherein you will be told to maximize or minimize something, and you will be given some constraints. And combinatorial problems are basically problems wherein you will be told to count, give a number of times something can happen. That is a combinatorial problem. So broadly, if I get a problem which falls under one of these two categories, I will think of applying dynamic programming. So that's the first thought. So this question falls under which category? Does it fall under any of these category? If it does, under which category does it fall? Optimization. Yeah, you have to maximize the total amount of money that the robber can rob from the house. So it falls under the optimization category, and from there I infer that I will at least try using dynamic programming for this question. Okay, so now I have yeah, Harsha, do you have anything? You raised your hand.
Sir, then how do you between greedy algorithm and dynamic programming?
We will come to that. We will come to what greedy is. Don't worry. First, we will explain dynamic programming, and we will come to the greedy algorithm in the third class, maybe. Okay.
Okay, sir.
Yeah. So this is the first thought that came, that I will use dynamic programming. Now, when I am about to use dynamic programming, there are certain things that I will look at. First thing is, I will look at the problem and try to enumerate all the variables in the problem. So what are the variables in this problem? You have an array, you could say, the list of houses. That is the only variable that you have in this problem. Correct? This is fine. Everyone understands? You don't have any other variable. You don't have any integer that is given, or you don't have anything else that is given. You just have an array which is given. So you just keep in mind what are the variables that are given in the question. This will be handy when we are, or this will be useful when we are constructing a representation for the problem, which is what we will do. But before that, once we keep this in mind, we will think about a decision that we can make at this stage such that we can, so we want to make a decision as at this stage such that we are left with a different problem or a smaller instance of this problem. This is the next thing that I will do once I have the problem and I know what are the variables in the problem. So this is probably the most crucial part of dynamic programming, recursion as well, that what is the decision that you can make at this stage such that you are left with a smaller instance of the problem. And my whole idea, or most of the time that we will be looking at dynamic programming, I will be showing you the different types of decisions that come up in these problems. So here, one decision could be that obviously the robber is here and you have a list of houses lined up. The robber will go to the first house, right? And he will either rob the house or not rob the house. Correct? So that is the decision that the robber can make here, that he will either rob the house or not rob the house. That's one. Yeah, it is include, exclude. I will show you this question can be done through another decision also, which we will see. So now let's say the robber goes ahead with the decision of robbing this house. Then what is the money that he has gathered? He would have gathered 32, correct? And now you know that if he robs 0, he cannot rob 1 because of the constraints of the problem. So what is he left with? He is now left with this portion of the street that he has to rob, correct? So he is left with now array 2 to n minus 1. So whatever money he can get from this plus 32 will be the total amount of money that he can make if he goes ahead with the idea of robbing the house, right? Is this clear to everyone, the first part? Others, is it clear? Yeah. So now what is the other decision? He can choose to not rob the house. If he does not rob the 0th house, then what is he left with? He did not get any money so far, but now he is left with array 1 to n minus 1, and whatever maximum money he can get from that plus 0 will be the total amount of money that he can get if he does not rob the house, correct? So what is the maximum money that he can make? The maximum money that he can make will be the max of these two, T1 and T2, right? Do you understand this? So this is the decision that I made. This is one of the decisions that I showed you, which is basically take it or leave it, or include or exclude. And using that decision, basically our problem reduces to, if he chooses the 0th house, then he has 32 and he is left with this part of the array 2 to 4. And if he chooses not to rob 0th house, then he is left with 1 to 4. Whatever money, maximum money he can get from 1 to 4, that will be the total maximum money that he makes out of all the houses. And in this case, whatever maximum money he can get from 2 to 4 plus 32 will be the total money that he can get from all the houses. So this is the decision that I made, and based on this decision, this is what I arrived at. Now, if you understand this, then the third step, once you know the decision, is understand the sub problem that you are left with after making the decision. Harshal, I'll take the questions after the end of this illustration, okay? So the next thing is we want to understand the sub problems that you are left with after you have made the decision. So let's see. what is the, you had two types of decisions that you could have made here. One was either include it. If you are including it, you are left with array 2 to n minus 1. If you are excluding it, you are left with array 1 to n minus 1. Okay, so the sub problems that you are left with is this and this. Now the next thing is, try and understand the relationship of this sub problem with the original problem. So your original problem was the entire array. What is the sub problem that you are left with? You are left with this in this case, and in this case you are left with this, right? So the sub problem that you are left with in both the cases is a suffix array of the original array, right? Everyone understands this? So once you understand the sub problems that you are left with, the next step is try and obtain a representation for the sub problem. Now this is, so 3 will help you in obtaining a representation for the sub problem. So in 3 you realize that it's a suffix array of A. So the representation for this sub problem, how can you now represent a suffix array of a given array? Using an array and a start index, right? So you can use this to obtain a representation for the sub problem, correct? Now after this, what you should do, or what you could do is, so now you know, now you draw the recursion tree. So that's the 5th step. So let's see the recursion tree for this, and we will try and formulate it better. So what was the recursion tree? You had the entire array, and you said that I could choose to include this 32 or not include it. If I don't include it, then I'm left, if I include it, then I'm left with 2 to n minus 1. If I don't include it, then, so this is 32, I include, or let's call it plus, and this is minus, that you don't include it, then you are left with 1 to n minus 1. Now do the same exercise one more level. Just do a couple of levels. You will try and understand. You will get an understanding. So let's include what is that. Now for solving this sub problem, again you will employ the same technique, which is basically you can choose to take the first element or not take the first element. If you take the first element, then you are left with 3 to n minus 1. If you don't take the first element, then you are left with 2 to n minus 1. Just do the exercise for one more level here. If you include it, you are left with 4 to n minus 1. If you exclude it, you are left with 3 to n minus 1. So now see, now from here, if now from here, see this and this, aren't they the same sub problem? Similarly, if you see this and this, aren't they the same sub problem? Right? So when you are solving for this part of the problem, you are solving for 3 to n minus 1. Now when you are solving for this part of the problem, you are again solving for 3 to n minus 1. So from here, I will conclude that I don't need to solve 3 to n minus 1 twice. I can just solve it once and use it in both the places. Correct? Do you understand this idea? How many of you understand this idea? So from here, I conclude that my sub problems are repeating. Yes, this is what is called overlapping sub problems. So from here, I conclude that my sub problems are repeating. So I don't want to solve the same sub problem again and again. Instead, what I will do is I will solve one sub problem exactly once and use it whenever I have to solve a bigger problem. So now that is the key idea here, that I will solve a sub problem exactly once. Or at most once, and use it whenever I have to solve a bigger problem that uses that particular smaller sub problem. Now, once this idea I have in mind, so let me just give you a summary of what all I have done so far. So I told you that we want to use dynamic programming. How did we arrive at that? We saw an optimization problem, and I told you broadly there are two types of problems that can be solved using dynamic programming: optimization problems and combinatorial problems. So we saw an optimization problem and we concluded that let's try dynamic programming on it. Now, when we are trying dynamic programming on a question, the first thing that you should do is just look at the problem and look at all the variables that are there in the problem. Just keep them in mind. And the next thing that you should do is think about the decision that you can make at this stage, just at this stage. And here we looked at a decision which was include or exclude. So the robber can choose to include the 0th house or exclude the 0th house. Once we have made this decision, we basically write the recurrence. So recurrence is basically the relationship between a bigger sub problem, relationship between a problem and its sub problems. So that's the next step that you do from the decision. And we arrived at a decision that the recurrence is that if T denotes the total, the maximum that the robber can rob from all the houses, then this is maximum of T1 and T2, where T1 was basically 32 plus whatever you can get from 2 to n minus 1, and T2 was 0 plus whatever you can get from 1 to n minus 1. So from here I arrived at recursion, the recurrence, that this is how I can obtain this is the relationship between my original problem and the smaller problems. So this is a smaller problem, this is another smaller problem, and this is the relationship between them. So from there I write the recurrence relation. Once I know the recurrence relation, what I will do is I will draw the recursion tree to check for overlapping sub problems. So I will draw maybe a couple of levels to check whether there are overlapping sub problems or not. And I check that I see here that when I am from the recursion tree, I saw that the same sub problem is being solved more than once. So from there, I realized that I have a overlapping sub problems which I need to take care of. So this is all that I have done so far. Is there any question till now? I'll just take a pause. Does everyone understand whatever I have done so far?
Sir,
Most of it is from recursion only. Yeah, Ritik.
Sir, this is the top to bottom approach you are discussing, right?
No, I have not used any top to bottom, or I have just told you how to go about. I have not discussed about top to bottom or bottom to up yet.
Sir, because like when I was thinking, I came up with a different approach, which was not different, somewhat different from this. We were computing from A0 and A1. You know that approach. So basically, how can we think? What approach should we prefer?
I have just told you one approach, right? Which is basically this. Like we will now decide whether we want to use top to bottom or bottom up or top down. We will see.
So another approach which I am seeing is that we can store zero in, like we can make an array A0, A1, A2, A3, and a sub problem can be basically the maximum value which we can get up till a certain point.
We will see. That's the sub problem here also. We will see. The decision that you are talking about, we will take up that decision also. In whatever you are saying, the only difference wherever, if you have alternate solutions, will be at the decision level. Like it will only be here that you might differ.
Okay, so any decision might work, right? We don't
Yeah, as long
need
as
to...
it is correct and consistent, it will work.
Okay.
So now, till now, I know that we have overlapping sub problems. So now what I will do is, now I have two ways to go about solving this. Let's talk about the first way. You can now go about solving this. So now you know that you have a bigger problem which you wanted to solve using smaller problems, and you realize that the same smaller sub problem is being solved more than once. So you said that I will not repeat the solution. Instead, what I will do is I will solve it only once and use it to solve it only once. So first way you could do it is you could solve so now you could solve sub problems starting from the smallest sub problem. And gradually building up to the biggest sub problem. This is one way you could do it. So you say now that what I will do is I will solve the smallest problem. Then I will solve a problem which is one bigger than the smallest problem. Then I will solve a problem which is one bigger than the previous problem, and so on. So I will solve problems starting from the smallest to the biggest. So finally, when I am here, I would have solved the original problem. This is the order that I want to use to solve the actual problem. So if I go ahead with this strategy, what is the smallest sub problem that you could have for this problem? What is the problem? What is a problem here? What is a sub problem here? A sub problem is a suffix array, right? So what is the smallest sub problem that you could have? Yeah, size 1. It could be this, only one house. Correct. So what I will do is I will solve the problem so now the order that I will do is I will solve for, so think about this now. This is the entire array. This is the smallest sub problem. Correct. This is the next bigger problem. This is the next bigger problem. This is the next bigger problem. Then this is the next bigger problem. Then this is the next bigger problem. Do you understand this? This comes from the fact that the subproblems are suffix arrays. So the smallest suffix array is this, then the next bigger suffix array is this, then the next bigger suffix array is this, then the next bigger suffix array is this, and this way. So if I am using this strategy of solving, I would first solve for this subproblem. So what is the solution for this subproblem? You could either, so what is this subproblem? This subproblem is array n-1 to n-1. You just want to solve for this. And what is the solution? Because the money is all positive, if you are given only this house, the last house of the array, what would you do? You would simply rob it. There is no other constraint, right? So here the answer for this, the smallest sub problem, is the value of the array itself, right? So that's the first thing that I would do. I would solve the smallest sub problem. That's the first thing I have done. I have solved the smallest sub problem. You will understand why we want to solve like that. Now what we will do is, now we will go about solving the problems in this order. Now we will solve problems in an increasing order. Using the same recurrence. Using the same recurrence that we devised. So now let's see. Now your next bigger problem is this subarray, this suffix array. So how would you, so what is that array? That array is basically an array of size 2. This is n minus 1, this is n minus 2. Correct? So you have some values now. Let's say you have 14 here, you have 16 here. So now, how would you solve this sub problem? You will use the same relationship, same decision that you made, that you decided on, which is basically, I can either choose to include this or exclude this. So if I choose to include this, then I have 14 that I can take, and I will not be able to rob this house. So now I am left with nothing else. So the maximum amount of money that I can make with this is 14. Right? And if I choose to not include it, then what is the maximum amount of money I can make? That is equal to whatever money I can make from this. And so whatever money that I can make from this, what is that? That is a smaller problem of this problem. This problem was of size 2. Now you are left with a problem of size 1. And remember that you had already solved a problem of size 1. So you will simply use it. So here you will say that T2 is, if I don't include 14, basically it is 0 plus whatever is the solution for the first, a sub problem of size 1. And this I know I have already solved it, which is in the first step. And I know that this was 16. So now I know that for this problem, the answer is max of T1, T2. So this is max of 14 and 16 and 16. So for this, a sub problem of size 2, my answer will be 16. Correct? Do you understand this? Everyone understands this? Ayush Misra, are you following? Alisha, are you following? Aryan, Divyanshu, Drishan, Harika, Meet, is this making sense? Yes. Okay. So now what I will do is, now I will move on to the sub problem of size 3. So this is the sub problem of size 3, n minus 1, n minus 2 and n minus 3. So let's say you have a 12, you have a 14 and you have a 16. So what will I do? I will use the same decision. So for solving this, because this is also a problem, it's just a sub problem of the original problem. So I can use the same decision that I used for the original problem. So I will go here and I will have two decisions. I can choose to either include 12 or not include 12. If I include 12, then what am I left with? If I include 12, then I will have 12 and I will be left with whatever solution I can obtain from this part of the problem, from this sub problem. And I have already solved this, right? I solved this in 1. So for this part, I know the answer is 16. So the total money that I can make is 12 plus 16, which is 28, if I include 12. If I don't include 12, then I cannot make any money from this index. But what am I left with? I am left with this sub problem now. And because we are solving sub problems in an increasing order, this sub problem I have already solved, right? And which I solved here, right? And I got a 16 as the answer for this sub problem, right? So I will simply use it. Correct? So the total money, so the now for this entire problem, what is the maximum? 28 and 16, it is 28. So for this sub problem, my answer is 28. And in this manner, I can keep building. Now I will go to sub problem of size 4 and make the same decision at this. When I include it, I will be left with this sub problem, which I have already solved. When I exclude it, I will be left with this sub problem, which also I have already solved. So I will simply look up both the values and use them to obtain the solution for this sub problem. And I can keep increasing. Now I will go to 5, then 6, then 7, and so on. Finally, once I have gone to size n, I would have the answer for the original problem. So this is a linear way of solving, wherein we are starting from the smallest sub problem and we are solving problems increasingly in an of increasing complexities, one after the other. So once we are done with the smallest, we are solving the next smallest. And when we are solving the next smallest, we know that every time we are using a smaller sub problem because of the recurrence. So that's why this is helping us, because whenever I am solving a sub problem of some size k, I will be using sub problems of size less than k. And I have already solved them because this is the approach that I'm using, from the smallest to the biggest. So I will simply use them. Right? Does everyone understand all the story that I did here in number 7? So now let's see. So when you are solving, so now let's see, when you are solving a problem, what did you do? You said that I will use this paradigm that where I will solve problem incrementally. So when you are solving this problem, what all the next step is to figure out which smaller sub problem do you need when you are solving a particular bigger problem. So for when I'm solving this problem, I would need this or I would need this, right? So can I store all the sub problems in an array or in a data structure such that when I am solving a particular problem, I would have already solved the smaller sub problems which would be in this array and I can look them up? So that's the next thing that I will think about, is that how can I store these sub problems? Because when I'm solving a particular problem, I am using the solutions of some smaller sub problems, right? So I need to look them up. So the next thing I'm deciding is how can I store them? So how does the sub problem filling looks like for us? It is this, then this, then this, then this, then this. For all these you are storing values, right? So can you store them in an array such that for this you use this index, 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 and so on. So then when you are at a given index I, when you are solving this problem, let's say this index is I, you can simply look up I plus 1 and I plus 2 in this array to obtain solutions for this problem and this problem. Do you understand this? So how many of you understand this? Now I am just, once I understand the structure of the sub problem and how the order in which I am solving the sub problem, what I am doing is now I am thinking about how can I go about storing these sub problems, because I am looking them up, right? So that decision I made that these are the sub problems, so I can store them in an array. right? So when I'm solving this particular sub problem, I can look up this and I can look up this to obtain solutions for the smaller sub problems, and then I can solve this problem, and then I can update this index here. Correct? So I can keep building this array, and this array is what we will call the DP array. So that finally, once we have built the entire array, it would mean that I have solved for the final bigger array also, which is from 0 to n minus 1. Right? And so now if I call this array as DP, DP of 0 will give me the solution for the will be the answer. Correct? So that's basically the approach that we will use. So this is the entire solution. Now you can ask me questions on any part of this solution. I can summarize what we have done. We first formulated a recurrence by deciding. We made a decision. Based on that, we formulated a recurrence. Based on the recurrence, we drew the recursion tree and found out that you have problems which you are solving, same problem which you are solving more than once. From there, I said that I need to store the sub problems. So there are two key things here. When I'm storing the sub problems, I would need to decide the order in which I am solving the sub problems. And here we said that let's look at one technique wherein we will solve from the smallest to the largest. And once I know the order, the next thing I will think about is where can I store the sub problems, or how can I store the sub problems, or how can I store the sub problems. So there we made this decision that let's store it in an array, and this is how we will store the sub problems. And from there, the final step was what is the final answer. So the final answer we said was DP of 0. So any questions in any of these steps 1 to 5?
Sir, this approach was totally clear. I just wanted to know what is the difference what is the difference in the decision or any such step in where we iterate this array?
So the decision will typically determine your sub problem, right? Here your decision was such that you had 1D sub problems, one-dimensional sub problems. You had suffix arrays as sub problems, right? So those
Yes,
sub problems came from the decision. You could have complicated decisions such that your sub problems are not 1D. For instance, you could have a decision like which is the first house that I will rob. I'm just giving you an example where your decision making could be. So let's say your decision is that which is the first house that I will rob. So you can say that I can rob 0, or I can rob 1, or I can rob 2, I can rob 3, any of the houses. So let's say I rob the ith house. So when I rob the ith house, what am I left with? I am left with 0 to I minus 2 because I cannot rob I minus 1. And I am left with I plus 2 to n minus 1. So these are the smaller sub problems that I am left with now when I rob the ith house. So now what are these sub problems? Are these general one-dimensional sub problems? No, these are actually sub arrays, right? So now now once you have sub arrays, your sub problem space becomes larger because these are where just suffix arrays. There were a total of n such sub problems. Here you will get a total of n square such sub problems, and you have to do it for all the i's. So the total complexity of this question becomes n cube, and the DP array is of size n square if you are making this decision.
Sir, we will be doing it for all the arrays, that will be n, and we will be storing it, so that will be.
You will be storing all of these sub arrays. For all these sub arrays, you will be storing the solution. So that will be the decision was which house I am robbing first.
Sir, how is it n cube? I didn't get it. The complexity
So
n cube.
what is the recurrence? Think about the recurrence for this entire relationship. The answer is basically maximum of across all I. If you are, let's say you chose house I as the first house, then you will be left with t0 to I minus 2 and t I plus 2 to n minus 1, right? And plus ai obviously in both the cases, and maximum across all the i's, and you have a max here, you have this plus this, right? This is the recurrence, right? So t, if t denotes the total you can get by robbing all the houses, it is basically t of 0 to I minus 2 plus ai plus t of I plus 1 to I plus 2 to n minus 1, right? This will be the total how amount that you can make, and you will have to maximize this for all I. Right, Ritik? Do you understand this recurrence?
So it will be n square, right?
This will not be n square. So each of these now are, this is a sub-array. So you will have to solve it.
Okay.
So these will a total of n square such. And for any sub-array, you will be using n steps. This is the n steps here. So it will be n cube.
Okay. Got it.
So that decision making will influence typically everything later that you do.
And sir, if we make a decision as a for a particular I, we compute the maximum possible value which we can get up till that particular I. Basically, a prefix sub problem.
That's what
Then
we made here, right?
yeah. So that's the same, right? And we return dp n minus 1.
That's what we are doing. Yeah, it's just that you are doing a prefix. I am doing a suffix. It is the same. So your decision was the robber can choose to choose to rob the n minus 1th house or not rob the n minus 1th house. So when he robs the n minus 1th house, then he is left with 0 to n minus 3. If he does not rob it, then he is left with 0 to n minus 2.
Yes, sir.
So
And
those
we
are
store the
prefix
maximum.
arrays. Yeah, I mean it's the same. And you take the maximum both of them. So it's the same decision, just that you are starting from the n minus first out. You can start from any of the other ends, any of the ends. Is step 1 to 5 clear to everyone? Can I have acknowledgement if it is clear? Yeah?
Sir, here in the DP array,
Mm-hmm.
While storing the value at the last index, do we store the value of only that particular element next to the next element, or the both, including the last and
No, we will see. It's the maximum. I will formulate that. So from here, we know that this is the DP array. So what is DP of I actually denoting in English? DP of I is actually denoting the total or the maximum that you can rob from houses I to n minus 1. Right? That is what DP of I is denoting. And from there, you can say that your answer is DP 0, the maximum that you can rob from 0 to n minus 1. So you compute DP of I. How do you compute DP of I? You use the recurrence, right? So DP of I is maximum of, you either include I or not include I. So if you include I, it is AI plus DP of I minus I plus 2, right? And if you exclude it, you have DP of I plus 1. This is how you compute the DP of I. Whatever I said in English, I have just written it down mathematically.
So why do we need the DP? We can just maintain, because we are only using like two previous elements or two formula
I will
elements.
come
We
to
can
that.
use
Just two variables we can use, yes. We will come to that also, which is the state space optimization basically. right? Karan, do you understand this?
Sir,
Mhm.
sir, you told something will be of order of n cube. What was that?
It's okay. I mean, let's discuss that after the class. Okay. That was just one another type of decision which could give you an n-cube solution. We will see that. Don't worry. So let's quickly solve this question using this decision, and then we will come back and stare more at this. So let's say this is the, so what is my, I know what, so from here I have determined that I need to populate the DP array. It's a 1D array, right? So I need a DP array, which is a 1D array. And what is the size of that? It is the size is the same as the size of the array, the original array. So let me declare a DP array of n. You could declare it of n plus 1 also, which is fine. Now you know that you are solving from the smallest subproblem to the biggest subproblem. So the first step is solve the smallest. And the smallest subproblem is generally a problem for which you would have the solution at hand. So what is the smallest subproblem? N minus 1, right? Which is just one size. And for that one size, it will be whatever the value is. Correct? Now you will iterate from the smallest, from the next smallest problem to the biggest. And populate. So let's do that. So what is the next smaller problem? It is n minus 2, right? And I will keep going till 0. How do I solve this? I know that there are two choices. One is I can exclude it. So if I exclude it, what am I left with? So dp of I is what I'm trying to populate. If I exclude it, I will be left with I plus 1, right? And the second is if I include it. So if I include it, I will just take this case that if I plus 2 is less than n, then only I will do that. Then dp of I is maximum of whatever I have so far. And if I include this, I will have nums of I plus dp of I plus 2. Right? So I just need to take care of one corner case, which is for this, exactly for this n minus 2. I have a corner case that I plus 2 will become n, right? So I need to take care of that. You could take care of that in this manner, or you could do it in other neater ways also. You could have an array of size n plus 1 also, but that's not the point here. Let's do it in this manner. And then I can return simply dp of 0. So that's basically what for an empty array. Just take care of that. Okay. So look at this solution and ask me questions if you don't understand any part of this question. Another way you could have done this is you could have had a DP array of size n plus 1 initialized to 0. So then you have two sub problems that you are solving. The empty DP of n is an empty subarray. So for an empty subarray, you will have 0, and DP of n minus 1 is basically a subarray or a suffix array of size 1. So that will be nums n minus 1. And then you could simply have excluded this and just did this. Then that would also have worked. Okay, is this clear? Can I have acknowledgements if all this is clear? Is there any question on this? People who have seen DP very rarely, do you get a feeling for this?
Yes, sir. Sir, how can we do this question recursively?
How can we do this question recursively? You mean we will look at the other way. I know what you're talking about. You're talking about memoization, right?
Yes, sir.
So we will come to that, don't worry. Order of exclude and include is important. I did not get the question.
Sir, so the choice between first we excluded, then we included. Do we have
No, it does not matter.
exclude first and then include?
No. You could simply have removed all this. Just write DP of I is max of. You either exclude it. So this is the one. Or you do include it. This is also fine. Okay. It is the same.
Okay, sir.
Yeah, it really does not matter. Why will it matter? Maximum is you just have to take the maximum of those two. It does not matter. Okay, so this is one way you are doing it, wherein you are building the subproblem from the smallest to the biggest.
Sir, does the nums of I is the value at that particular index?
Yeah, I mean, that's the array, right? That's given to you.
Yeah. Okay.
So nums of I is the value at that index. Okay. So now let's see. This is one decision. Okay. And didn't get what's the difference between both approaches. What is the other approach? I did not tell you any other approach. I just told you one approach so far.
Approach in the sense you wrote two kinds of things, right? While include and exclude.
Come again?
Approach in the sense you wrote three kinds of solutions, right?
Yeah, those are just implementation differences. Like everything is whatever I have discussed in this board. It is the same solution. I have just implemented it in different ways. So what I did was so the problem is when we are solving for a subproblem of size 2, we are solving, then if we don't include this, then we are left with this problem which we have solved. But if we include this, then we are left with an empty subproblem, right? So I just, in the first approach, I exclusively or explicitly had an if for this case, that if it's an empty subproblem, then don't add anything, just add this, right? And if it is a non-empty subproblem, then the result is this plus whatever is after. That was the first approach. Then the second approach, what I did was I created a DP array of size 1 more than the size of the array, to signify that DP of n is basically the solution for the empty prefix array, empty suffix array. And I said that DP of n is 0, which basically meant that for the empty suffix array, I have stored 0 value. And n minus 1 is a suffix array of size 1. So I just stored nums of n minus 1 here. And then I can just comfortably compute for any index, right? For this also, when I'm computing, I'll be using this I will be using this basically, or I will be using this. That was the second approach. The third approach was just, I did dp of I, it is basically max of these two quantities, right? So I just did it in phases, wherein I just initialized dp of I to this. And then in the second step, I took a max of whatever was there in dp of I with this.
Yes,
So
sir.
those were
Got
1,
it.
2, 3. Like it, all of them were different implementation. Nothing fancy in that, and not important also. Like you could do any of them. It's not really very important. Okay. So this is one. Now let's say, let's do another decision. So now you understand that the decision is heavily influencing the type of sub problem and the complexity of the problem, right? So now let's say we are trying to do another type of decision. I will give you the decision. This is also a very standard decision that is used in a lot of questions. Let's say I am saying that my actual, so now let's see. This is the house. This is the total house that I am. Now listen to this decision very carefully. This is needed in a lot of cases. So let's say the robber is here. I look at all the houses that the robber would rob. What is the, I look at the solution. And I say that in the solution, you had some houses. Let's say you had A1, you had A4, you had some AI, you had some AJ. These are the houses that the robber robbed in order to get the maximum money. Okay. So now I could make a decision of this type, that assuming the robber always robs the 0th house, what is the total amount of money he can make? So the decision is that assuming the robber robs the 0th house, what is the total amount of money that he can make? That's basically the question. So if this is the decision, then what is the sub problem? Let's first look at two things. If this is the decision, then what is the sub problem and what is the actual answer? How do you arrive at this solution? Okay. So if this is the decision, that assuming the robber is robbing the 0th house, what is the total amount of money that he can make? It is basically A0 plus the solution to this problem, which was dp of 2 to n minus 1. Correct? So assuming the robber robs the 0th house, this is the total amount of money that he can make. Is this clear, first of all? Just the recurrence, that assuming that the robber robs the 0th house, what is the total amount of money that he can make? So if you understand this, then what is the actual answer? In the actual answer, the robber would have robbed at least one of the houses. So now what we are saying is, in the actual answer, look at the first house that the robber robbed. That first house could be this house, or it could be this house, 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 it could be any of these houses. Correct? So if this is what I am calling dp0, dp of 0 is basically assuming the robber robs the 0th house, what is the total amount of money that he can make? Then my actual solution is maximum of all dpi for all I. Why? Because I'm saying that whatever the first house is, it can be the 0th house, it can be the first house, it can be the second house, it can be any of these houses. The first house that he robs, if we line up the houses in an increasing and number them in an increasing order, then the first house could be any of these. So let's say this is the first house that he robs. So if this is the first house that he robs, then dp of I is basically giving me the total money that he can make, assuming he is robbing the ith house. Total money that he can make from this, assuming that he is robbing the ith house. Right? So won't dp of I be the answer if house number I is the first house that he is robbing? Did you get this? How many of you understood this? I told you two things. I told you a decision, and from that decision, I just gave you a recurrence relation. That was the first thing.
P of I store, it stores like from 3 till n minus 1. What is the maximum value, right?
From 3 to n minus 1,
If I equals to 3.
If he assuming that he is always robbing the third house.
Yes, so it is from 3 to n minus 1, right?
Yes, yes.
So, but then you're saying dp of I is the answer, but then we can also rob 1 or 0.
That's what I'm
So
saying.
have
It
to
could
add
be,
that.
it is the maximum across all I for maximum of all I dpi.
So 3 is the first house that he
First
robs,
house
right?
that he is robbing, I'm assuming that.
Then
So
it's
then,
the maximum.
yeah, then it is basically dp of 3, right? And dp, the definition of dp is that it is dp of I is the, assuming that he always robs the ith house, what is the total money that he can make for house I to n minus 1. Did you get it? So I just told you two things here. I told you that if I use that definition, that if my decision is that let me look at the first house that the robber is robbing, that is my decision. So the robber could rob this house or this house or this house or this house. He could rob any of these houses. Any of them could be the first house that he is robbing. So let's say the ith house, if this is the first house that the robber is robbing, then what is the total money that he can make for the entire array? He will make basically ai plus whatever he can make from dp of I plus 2. Right? So this will be dp of I, where, and now your total answer would be maximum across all dpi for I 0 to n. Yes, total money robbed from houses I to n minus 1, including the ith house always. Ishan, this is clear? He can also select 0. What is that, Karan? Select 0 as in? Yeah, he can select. So that's what it is, maximum. So the first house that he can rob can be any of these. So if he robs the first house is 0, then the answer is dp 0. If the first house that he robs is 1, then the answer is dp 1. So I'm saying that whatever answer is the eventual answer is basically the maximum for all these arrays, because dp of 0 is assuming he robs the 0th house. dp of 1 is assuming he robs the first house. So any of these houses he could choose as the first house.
Is this another way to solve the previous question, or?
Yeah, it's the same.
Okay.
Another way to solve the previous question only.
Sir, how can you say with certainty that whenever we rob I, we need to rob I plus 2?
We don't need to rob I plus 2.
you are computing it as that, right? dpi is equal to ai plus dp of I plus 2, where dp suggests that we are robbing that particular index. So whenever we compute dp of 1, we will compute it as a1 plus dp of p. So it considers only that possibility that we are robbing 1 as well as we are robbing 3. Whereas the possibility of robbing 1 and not robbing 3 is not calculated, I guess.
So robbing 1 and these are all positive numbers, right?
Yes, sir. So there might, I think there might be a case where suppose we have array as 1, 2, 1, 2, 1 and 4. So doesn't robbing 1 and 4 help rather than robbing 1 and 1?
No, for this you will get an answer of 6 in any case.
Sir, take 2, 1, 1, 2.
It's the
Yeah, take 2, 1, 1, 2.
okay, 2, 1, 1, 2.
Then in this case, we will be considering only 2 and 1 and 1 and 2, but the answer should be 4. Because
Yep.
If we are considering, come again for this test case, which index are you considering currently?
sir, if we take the first element and according to our recurrence, we'll be taking the third element also, or either we'll be taking the second element and the fourth element. But the answer will come from taking first and fourth element, not either of the before. So
Compute the DP array for this. You will get it as, I guess.
No, I got it.
Yeah.
Yes. So basically the decision itself is wrong here, right?
Yes, sir. Because you are forcing us to rob I plus 2 whenever we are robbing I. That might
like
not
it
be
is
the
not
case.
necessary. So it is like not necessary that we have to jump into I plus 2. It could be I plus 3 or I plus n, and from that we have to find the maximum. Like it is mentioned in the question that it should
No,
not
sir,
go
but
to
I
the
think this
adjacent.
should work because DP of I plus 2 is the maximum of all the subarrays, right?
No,
So
it's not
DP
the
of
maximum.
Not
DP of
necessarily.
I.
Not
Considers
necessarily
only
maximum.
that possibility that you are
Acha, okay, I
taking
thought it.
No,
Okay,
this
okay.
will
I
not work.
and then.
Yeah. So,
So, sir, what
the
we have to
modified,
do, I think I got what we have to do. We have to make a new DP instead of DPI plus 2, which followed the previous question's conditions. So that will work, I think.
You can simply take the max.
yeah, I mean that's what here you can take the max. If you are always including I, then it will be maximum for all j from 2 to whatever some number I plus j. You have to take that here. Right? That's what you are saying, Ritik, right?
Yeah, but computations will increase.
But this will be n square now. This will be
Yes,
order n square, right? For a given I, you are using, you are not computing in
Sir,
constant time.
why are we
So
doing
we could
this?
just update
We
the
can
DP
just,
array.
yeah, that is what I mean.
We could at every step we could just maintain the maximum. Instead
Yeah,
of that, we could
that
just
was the
maintain the
exact-
maximum.
Maximum as in?
So
that
like
was-
DPI would be the maximum value of DPI and DPI minus 1.
The same approach which we used
Yeah. So
in
you
the
could,
reverse order.
you would, so this basically what you are saying is this could be done in order 1. You just
Yeah, yeah.
keep the maximum.
Yeah.
Yeah, makes sense. So did you get what is the flaw in this decision? Yeah. So, and did you get the updated decision? Does this decision make sense? So
Sir,
if this,
can you explain the order n? How we get this?
yeah, we will code it. Don't worry. So we will code it. So then you will understand the complexity. But the decision is that if you are including the ith house, or if ith house is the first house and DP of I is basically giving you the total money, that maximum money that you can rob, including the ith house, then that is basically AI plus either this or like all the subsequent i's, right? So the next number that you could include could be anything from I plus 2 to n minus 1. So now basically now let's see. So for a particular sub problem, so look at this now. Now that you are here, let's say you are solving for this particular problem, let's say. For this particular problem, what all do you need? You need the maximum that you have found till I plus 2, right? So when you are coming from here, you could keep updating the maximum, right? And that's what we could use in this place straight away with AI. That's what Gitansh was saying. Simran, do you understand this? So instead of, because we are building it from the right? From the smallest to the biggest.
Yes, sir. We actually storing the maximum value at I plus 2 location.
We are come again?
We already storing the maximum value of at I plus 2 location. So it will always be maximum for the that I plus 2 subarray.
Yeah, you could store the maximum basically. So then that is, so then your DPI is not including the ith. DP of I is, then you are saying that DP of I is the maximum that you can get till I, from I to n minus 1.
That doesn't this approach of computing DP in reverse order and not forcing us to consider I make it the same approach as what we did earlier, because the answer will surely be DP of 0. DP of 0 or DP of 1 basically.
Yes, you're right.
That's the same approach, I guess, no difference.
It is boiling down to the same approach, like with a different decision.
Sir, by this approach, how can we ensure that there are no alternative way?
There are no alternate.
Like they are not alternate houses.
That's what we are keeping. This is the maximum that we are keeping, right? So everything that we have gotten from I plus 2, which is the maximum. So from I, you could include I and you could include I plus 3. Yeah, it's okay. Let's discuss this approach after the class. Like this is a fairly, it's basically just beating that same approach to death. So it's okay. You can ignore it for all practical purposes. We will discuss it after the class. Okay. Okay, Karan. Let's do another question before we talk about another way of doing it. Let's do 213. So now the additional constraint that the question has, how can you do this? This is just a simple modification of the previous one. Yeah.
So like we have two cases when we are taking the first element and not taking the last, but basically robbing the first house and not the last house, and not robbing the first house and robbing the last house. So two DPs, basically from 1 to 0 to n minus 2, and another one from 1 to n minus 1.
Yes. So here the only difficulty is that now you are said that 0 is all. So this is a cyclic now. So 0 is there, then you have 1, then you have 2, and so on till n minus 1. So 0 is also considered adjacent to n minus 1 now. And now you have to solve the same problem. So what is the difficulty, or what is the what is the fallacy in the previous decision? The decision was that you could choose to rob house 0 or not rob house 0, right? So if you choose to not rob house 0, then you are left with this, which is fine. But if you choose to rob house 0, then you cannot rob n minus 1 also, right? Because now 0 is also considered adjacent to n minus 1. So that's where the previous decision fails. So we have to think of something else. You can divide this problem into two problems. Any solution that you take will either have 0 or n minus 1, right? It will not have both of them. Correct? So if it has 0.
So can there be a case when it has neither of them?
It can be, yes. Neither of them is also true. That can also happen. Like, but that will be a part of one of these. Right?
So, we can calculate this by considering 0 to n minus 1th element, like we will leave the last element, and once one go for leaving
1
the
to
first
n minus
element,
1.
1 to n.
Yes. And what is the intuition behind that?
We will leave one of the houses, adjacent houses, 0 or n, last house. Like we will initially take that we will not rob the house. Those are adjacent, like 0 or n, last house, n minus 1th house. So we will go from 0 to n minus 2 or 1 to n minus 1. Then we will not rob the two adjacent houses.
Yes. So we are basically breaking the cyclicity.
Yes, sir.
Right? This is like JE level. In JE also we used to do this, right? When we used to break the cyclic nature of. Did you understand this? So you can either choose 0, or if you're choosing 0, yeah. So see, what I'm saying is the answer for this is basically whatever you get from 0 to n minus 2, max of this, comma, whatever you get from 1 to n minus 1. That is the maximum, that is the answer basically. This is all that is there in this question. And for doing it from 0 to n minus 2, again, you could use the same approach. Now this is a linear array. For 1 to n minus 1, now you could use the same approach that we discussed in the first question. Why is it? Because if I take n minus 1, then I will not take 0. So definitely if I take 0, I will not take n minus 1. And if I take n minus 1, then I will not take 0. So whatever I get for this and whatever I get for this, the maximum of both of them will be the answer. Right, Jadav? Do you understand this? So this, as Ishan was asking, we are not including n minus 1, or we are not including 0 in the answer. We are just saying find the answer for this, whatever is the answer, and find the answer for this, whatever is the answer, and take the maximum. We are not saying that this particular for this particular array we are including 0. We are just saying that we can, whatever answer will be there will either have 0 or it will have, if it has 0, it will not have n minus 1. If it has n minus 1, then it will not have 0. So if it has 0, then it will not have n minus 1. So you can just find out the maximum for this, whatever it is. Right, Ishan? Does this make sense? Yeah, so this is this question basically. Yeah, it's just the previous question on these two arrays. Correct? Shall we move on? Everyone understands this? Let's move on to another type of decision that you can make. And let's use this question as the reference for that. 53. So in 53, what you are given is you are given an array of numbers, and the numbers can be positive and negative, all kinds of numbers. You have to find the maximum sum subarray in this array. So is the question clear to everyone? Correct? Now let's think about what kind of decision that we can make here. So for this is another type of decision that I will show you. For typical questions of this type of decision, think about the actual solution, the eventual subarray. That eventual subarray will end in one of the indices, right? So that eventual subarray, no, this cannot be done with 2 pointers because you have negative numbers also, right? So for this decision, yeah, let's understand this first, this algorithm. This is basically cadence algorithm only. But so for this decision, what are you, look at the eventual solution, and whatever that solution is, it will end in some index, right? That index could be this, or it could be this, or it could be this, or it could be this. It could be any of these indices, right? So if so let's basically then the decision, let's talk about the decision. The decision could be that what is the last element that you pick from this array? Okay. So what is the last element? That last element could be this, it 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 could be this, right? Let's say this is the last element that you pick. So if this is the last element that you pick, then what is the sub problem that you are left with? You are left with, so that if this is the last, then your answer is basically AI plus whatever you get for this part of the array, whatever maximum you can get for this part of the array, plus AI, that will be the answer. Let's call this S. For this part of the array, whatever maximum subarray that you can get with this as the last. So let me explain it in a more clear way. Like, this is not very concise. So I told you two things. One thing I am telling you is look at the eventual answer and look at the last index of that answer. That last index could be any of these. So if if the last index is this index, then can I say that if I compute the largest subarray for this particular part of the array with this as the last index, then that will be the answer? What I said is, for this particular array, if I compute the largest subarray ending at this index, if I am able to compute that, then that will be the answer, if assuming that the actual answer ends at this index. Do you understand this point? I said two things. I said, let's look at the eventual answer. That eventual answer will end in one of the indices, right? So let's assume that that eventual answer ends at index I. So I am saying that if for array 0 to I can find the largest subarray ending at I, largest as in the largest sum subarray ending at I, that will be the answer then. Do you understand this? Anyone else who understood this? So if I say that dp of I represents the, yeah, so I will do it for all possibilities now. So now I am saying that if dp of I is the length of the largest sum subarray with I as the last index, or including I, then my actual answer is maximum across all DPI. Right? Akash, is this correct? Anirudh, is this correct? So basically now what is the problem that I am left with? Yes, it will include num_i. That's what I'm saying. We are saying that look at the final solution and look at the answer. It will end in one of these indices. Let's say it ends at index I. So what is the actual answer? The actual answer is the length of the largest subarray ending at I. That is the answer. Right? So what I will do is I will do this for all the i's. I will do it for 0, I will do it for 1, I will do it for 2, I will do it for 3. And so for 0, I will compute the largest length of the largest sum subarray ending at 0. For 1, I will compute the length of the largest sum subarray ending at 1. For 2, I will compute the length of the largest sum subarray ending at 2. For 3, I will do that. For 4, I will do that. For 5, I will do that. For 6, I will do that. And I will, whatever, all these results, whatever I get, I will take the maximum out of all of them, and that will be my answer. Right? So this is the first line of thinking that I did. Right? So now, if this is the thinking, then what is the answer? The entire question is, the solution is basically, if you take the 0th path, it will be from 0 to 0. If you take the first part, it is from 0 to 1. If you take the second part, it is from 0 to 2. If you take the third part, it is from 0 to 3. Right? So if the actual answer ends at 3, I have to find the largest sum subarray ending at 3. So my sub problem is 0 to 3. If I take 2 as the last element, then my subarray, my subproblem is the largest sum subarray from 0 to 2 ending at 2. If I take 1, then it is the largest sum subarray from 0 to 1 ending at 1. And so on. So this is the recurrence tree. Now if you want to repeat, let's repeat one more level and you will get. So now for this again you will apply the same logic, that for this the largest sum subarray. Now, so that is the answer. Now let's see how do you compute the length of the largest sum subarray ending at I. That is the problem that I am left with now, right? So the first thing I did is I told you that my answer is maximum of all these, either 0, 0, 0, 1, 0, 2, 0, 3 and so on. So now what I am left with is the task of finding the length of the largest sum subarray ending at I.
Sir, we need to find the sum, so I guess it will be better to directly deal with the sums.
Directly deal with the
sum. We need to find the sum in the question. So rather than taking the maximum length and then computing the sum by iterating over that I and the length.
No, I'm not taking the, I'm saying that whatever is the maximum, I did not get your point. Like, we're not doing on length. We are saying if the answer ends at 3, then this is whatever is the maximum sum subarray ending at 3.
Okay.
If it ends at 2, whatever is the maximum sum subarray ending at 2, and so on. So now the actual problem that I am left with is 0 to I, right? If I am able to solve this for any I, then I'm done. So now let's see, how do you solve this? So what is the problem? The problem is I have to find the length of the longest subarray ending at I, right? So this, now here, this is where decision will come in. So this is basically in one, I just told you how I am looking at the actual problem. So I looked at the actual problem as the maximum for all these 0, 1, 0, 0, 0, 2, 0, 3. So till here I have not used any decision making or any dynamic programming. Now I come to the actual problem, which is for any array 0 to I need to find the length of the longest subarray ending at I. And for this, I will have a decision. So here I could make a decision that now the subarray will always end at I. So now the decision could be that either I have a subarray of length 1, which basically means that I have only AI in it, or I could have a subarray of length more than 1 ending at I. So in that case, what do I have? I have AI plus whatever the maximum length subarray I can get from this part ending at I minus 1. Right? So that itself is dp of I minus 1. So I will take the maximum of these two to obtain an answer for I. So I told you, let's step back. I told you two things. I told you that the first thing, I just looked at the eventual answer. And I said that my actual answer will either end at 0 or 1 or 2 or 3. So I have to find, for all I have to find the length of the longest subarray ending at that particular I. That was the problem that I was left with. So now when I said that, okay, now I have to find this. Now here, so for this now I will use dp. So this is the problem now. I have broken down. So if this is the problem, now I look at the problem and I say, okay, this is an optimization problem because I have to find the length of the longest subarray ending at I. So this is an optimization problem. So I might as well try dp. So if I'm trying dp, I have to come up with a decision. That's the next thing, right? So I will come up with a decision. The decision is here that I can choose a subarray of length 1 or I can choose a subarray of length more than 1. So if I choose a subarray of length 1, then basically my answer is only AI, right? If I choose a subarray of length more than 1, then my answer is AI plus whatever answer I can get from this part, right? Whatever answer I get from this part is basically the length of the longest subarray ending at I minus 1, right? So I am elongating that by adding AI to get the length of the longest subarray ending at I. So I can do that. Let's call this S. So that is the decision. From decision, I make a recurrence, which is basically I'm saying that whatever is the answer is the maximum of these two. Okay. And then the fourth part is I draw a tree just to understand the overlapping sub problem. So for this, let's just draw a tree. So we are saying that we want to do it for I. So we said that our decision is twofold. If we only have a subarray of length 1, then we don't have any sub problem that we are left with. If we do in a subarray of length more than 1, then it is basically AI plus what is the sub problem that we are left with? We are left with 0 to I minus 1. Right now, again, you can do two things. If you include only I minus 1, you are not left with any sub problem. If you do more than 1, then you are left with 0 to I minus 2 and so on. So this is the recurrence tree for solving I. Is this whatever I did so far clear? Is there any question on any of the steps? I will tell you the steps. The first step was I just reduced the actual problem to the problem of finding the longest subarray ending at I and taking a maximum for all the I's. And from there, I started my dynamic programming. So from 2, I said that to find the length of longest problem ending at I will use this decision. And I arrived at a recurrence and I arrived at a decision tree. Till here I have done. Is there any question so far for this question? Did you understand? Like,
sir, what does it mean by cross?
Cross is basically no sub problem. I'm not left with any sub problem. So if I choose a subarray of length 1, this is that sub branch, and greater than 1 is this sub branch. So I have to find a subarray ending at I. So if I'm choosing a subarray of length 1, then it's just AI, right? I'm not left with any sub problem. Correct? And if I'm going for a subarray of length more than 1, then basically whatever maximum sum I get from till I minus 1, I will extend that to include I. So the sub problem is this sub problem that I'm left with, which is basically for this sub problem, I need to find the length of the longest subarray ending at I minus 1 and add AI to that. Right? Can I know that you understand this? Yeah. So now everything will be taken care of, right? Why you started from 0 index, where, Karan?
Sir, in the recurrence tree, you have shown that all the starts from 0 to I minus 1, 0
Because
to I.
it is ending, I just said, ending at I. I want to find the largest subarray ending at I. Why I want to do that? Because I said that my actual answer is one of these subarrays. My actual answer will end at some index. I said that index could be I plus 1, I minus 1, I plus 2, anything. And I said I will take the maximum of all those. So I will take, so if I will take the maximum of. So this is the actual question. The question is you have to find a subarray, maximum sum subarray ending, maximum sum subarray, right? Within this array. So I said that that maximum sum subarray will obviously end at some index, right? So if it ends at an index I, then I am basically left with the task of finding the maximum length subarray ending at I for 0 to I. Right, Karan? So, and my actual answer is this line could be anywhere, right? This line could be here, 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 could be here. So I will take the maximum for all of them. Correct? So for 0 to I, this is what my recurrence tree is. Now, I will now do again for 0 to I plus 1 also I will do. Right? I will do for 0 to I plus 2. I will do for all the i's, right? So if I do for 0 to I plus 2, now what is I will make the same decision, which is either to include, go for length 1 or greater than 1. If I go for length 1, I am only left with ai plus 1. If I go for greater than 1, now this is the crux. I will have ai plus 1 and I will be left with 0 to I. Correct? So now for 0 to I, isn't it? Now you look at these two trees, 1 and 2. Hasn't this already, like, isn't this something that you are solving again? When you are solving for I plus 1, you will be solving I again, right? When you solved I, right? Similarly, when you will be solving for I plus 2, you will be solving I again, right? So this is where the overlapping subproblems are. Correct? So then I say that, yes, definitely these are overlapping subproblems. So from here, I will say that, okay, let's go about doing it in a systematic manner. Let's go from the smallest subproblem to the largest subproblem. So if you see, any subproblem is from 0 to some index j. So what is the smallest subproblem? The smallest subproblem would be, what is the smallest subproblem then? This one, right? So for this, it will be 0 to 0, right? So for this, what will be the answer? It will be nums of 0, right? Because this is including 0. The problem is I want to find the length of the longest subarray ending at that index, including that index. So I am including 0. So it's nums of 0. And then for nums of 1, when I am doing, so for this array, when I am doing, I will have these two cases. So I can choose to have only this. So if I have only this, then we will have, yes, we will take it, even if it's negative.
Sir, what is the second point you wrote? Like, could you repeat it? What?
Yeah, you understood this? How we...
Yes.
From the original problem, how we said that we are just left with, from the original problem, we are saying that we are just left with the task of finding the length of the longest subarrays ending at all the indices. We have to populate all the i's, we have to populate the length of the longest subarray ending at I, right? That was the problem that we are left with. So we said that let's do it, try it for I. So this is how the tree will look for I. Now we made a decision here, which could be either just have one array, subarray of length 1, or have a subarray of length more than 1. So we had this decision, and based on this decision, we solved it for I. Now when we are solving it for I plus 1, I again realize that I am solving it for I. So that is overlapping subproblems, right?
Okay.
And from there I come to this. So now I am going into with the strategy of building it from the smallest subproblem to the biggest subproblem. So the smallest subproblem is 0, 0. So for 0, 0, I can, my answer will just be num0, right? For 0, 1, what will be my answer? I will use this decision. So for 0, 1, when I am computing, it is basically the length of the longest subarray ending at 1. So I can only have 1, in which case the answer will be nums of 1. So let's say this was -3 and this was 5. So I can have 5, only 5. Or if I choose to not have that, then it will be this plus whatever I get from here. So what is the answer that I get from here? I have already computed that. That is -3. So I will do -5 plus -3. So from here I get a 2 and I will take the maximum of both of them. So 5. So till here it will be 5. Then I will go for 0 to 2 and I will take a similar approach. So for 0 to 2, let's say it is 5, it is -3, it is 5, and let's say you have a -2 here. So if you go for just one sized, then you will have -2. If you go for more than one sized, then you will have -2 plus whatever is the maximum for this. So what is the maximum for this? You already computed that, that is 5. So that is 5. So here you have 3. So for this entire thing, it will be maximum of this and this. So for this, it will be 3. And in this manner, I will keep incrementing. Now I will go for 4 and then I will go for 5, right? In this way, I will keep populating till n-1. And once I have populated for 0 to n-1, for all the indices, now I have populated it. So then I will just iterate over this and take the maximum. Does this make sense? How we defined the ordering? We defined it from the smallest to the biggest. And we said that this order will help us the same problem, basically the same approach we are using, which we used in the previous case. We said that we want to populate from the smallest subproblem to the biggest subproblem. And that's what we are doing here.
Sir, could you repeat why we are starting from 0 index?
Why, for a subproblem, why are we starting from 0? So how does your subproblem look like? Your subproblems look like anything 0 to I, right? It's a prefix array. Correct?
Yes.
So what is the smallest prefix array? It is 0, 0.
Okay.
So that's what we are using as the smallest. And then we are building up.
So if we made our decision at the starting point of the subarray, then we can make it
as a suffix array. Yes. Then you can make it as the suffix array. If you make the decision as the starting point. That's not really the decision. I mean, the decision is here. You can either have one size or greater than one size. That was just, so that was not really the decision. That was just a way of looking at the actual solution. So I looked at the actual problem and I said that that problem is nothing but taking the maximum of all for all these. So what is the time complexity? We will see. So let's see. So
sir, if all the elements are negative, then it will be the same logic.
Yeah. It will take care of all. If you have to find a non-empty, it will be fine. Even if it's empty, then also it's fine. Like this will take care of that case also. So if all the elements are negative, you will, so the actual answer is basically you are taking the maximum of all these i's, right? For all these i's, whatever answer you are getting, you are taking the maximum. So if all the elements are negative, then what will be the maximum? It will be the, like the cell with the least value or the cell with the greatest value in terms of, so for that I, you will get the right? So it will be fine. Just think from this level only. Yeah, the least negative value. So for a given I, what are the values you are using? You are using I minus 1, correct? So can I, when I'm doing this approach of going from the smallest to the biggest subproblem, can I keep storing each of them? So when I have the smallest subproblem, can I store it at 0? When I have this subproblem, can I store it at 1? When I have this subproblem, can I store it at 2? So if I do it like that, then when I'm doing it for 0 to I will basically be using AI, max of AI, comma, AI plus dp of I minus 1, right? Whatever I get from I minus 1 till here, I will use that. And so this, and I will update my DPI. Let's see the code. Things will become more clear. So here, what we are doing is, let's just, so we want to go from the smallest to the biggest subproblem, right? So what is the smallest subproblem? The smallest subproblem is 0, 0, right? So for 0, 0, let's store it at 0. For 0, 1, let's store it at 1. For 0, 2, let's store it at 2. So we will have an array, DP array of size n. First, the smallest subproblem. So for the smallest subproblem, you have DP of 0. 0 is basically just that number itself. Now what I will do is, I will go over the indices. So now when I am at 1, I am computing DP of 1, which is basically from 0 to 1, what is the maximum sum subarray ending at 1. So what will that be? So just write that DP of I is the maximum sum subarray for nums 0 to I in ending at I. So DP of I will be either 1 or more than 1. So if you are just having 1, you will have nums of I. If you are having more than 1, you will have nums of I plus DP of I minus 1. And what is your actual answer? The actual answer is max of DPI. So you could either run another loop or you could do it here itself. Both of them are fine. Let's try both of them. So let's say your result is integer minimum. So your result will be a DP of I. This is what I'm doing. You could get away with all this, the entire thing, by just doing it here only. And initializing result to also DP of 0. Okay, is this clear to everyone?
Sir, in the previous, like we discussed two approaches. Which one is this?
Where in the previous we
Like
just discussed
recurrence tree.
Mm-hmm.
Like which approach we used here?
We used
the first one, right?
I did not get your question.
like subarray of length greater than 1 and subarray length is equal to 1. We discussed two approaches
We
currently, right?
both the decisions we have used both the decisions, right? If it is a subarray of length 1, then you just have num psi, right? If you have subarray of length greater than 1, it is num psi plus whatever answer you get till I minus 1.
Acha, okay.
Yeah, so this is the decision and this is how you can do this question. Let's try another question. It is sort of the same decision. 152. So you have to find the maximum product subarray. Any ideas? सोचो, will the same method work? नेगेटिव नंबर्स भी हैं. So think about this. Your decision will change. So first line of thinking is, so the first thing is that what is my answer? Whatever my answer is, whatever is the maximum product that I will get will end at a certain index I. So basically, if I can find the maximum product subarray ending at I for all the I's and take the maximum of that, that will be my answer, right? So that was the first thing, same as the previous question. So I say from here, I determined that my result is basically nothing but maximum across all I, the maximum product subarray ending at I. Let's call that problem as PI. PI is basically the maximum product subarray ending at I. So I have to take the maximum for all across all I's. That is my thinking. Now from here, I know that I have to find this PI. So PI is basically the maximum product subarray ending at I. Right? And I want to find that. So how can I find that? what is the, now here we see that we have to find the maximum of something. So I will try dp. And the next thing is, if I'm going to try dp, what is the decision that I'll be making? So my decision is, again, it is similar. If I want to find the maximum product subarray ending at I, that product could be a single element or it could be a subarray of length greater than 1. So if it is a subarray of length 1, then it is nums of I itself. Correct? But now if it is a subarray of length more than 1 ending at I, what is the problem? So you have to find some subarray ending at I minus 1 and extend it. So now see, if this I can either be positive or negative, right? If it is positive, then you are good. Whatever the maximum product subarray you get ending at I minus 1, whatever that is, let's call it P prime, you could multiply that P prime to nums of I. And you will get the answer. If I is positive, right? You will get the maximum for I. And you can take the maximum of these two. Right?
That holds only when I minus 1 and I both are positive, right?
No. Forget I minus 1. I'm just looking at the sign of I. Whatever is the maximum product that I get till I minus 1, including I minus 1, I can multiply that with I to get the maximum product for I, which is of length more than 1. Right?
And what if the product until I minus 1 is negative?
That is fine, but it is the least negative. Whatever that is the least negative. So
okay,
it is fine.
Okay, the subarray starting from index 0, it is the prefix, right?
For this subarray, yeah. I mean, for this subarray, I am basically.
You are going forward, right? From 0 to n minus 1.
Yeah, I'm going forward. Same approach as what I had done in the previous question. So for I, if it is positive, I can find the maximum product subarray ending at I minus 1, whatever that is. I can multiply with it with nums of I to get a subarray of length greater than 1. And for subarray of length 1, it is nums of I. So I can take the maximum of these two, and that will be my answer for I. Right? Everyone understands till now?
Sir, is the P prime is product till that index?
It is till I minus 1, including ending at I minus 1. It is the same as what we did in the previous question. So in the previous question, we said that we want to find, if we are looking for a subarray of length more than 1, then we are saying we could either have a subarray of length 1 or more than 1. If it is of length 1, then I'm just using nums I. If it is of length more than 1, then whatever subarray sum I get, maximum ending at I minus 1, I can just sum plus nums I to that. Similarly, the same thing we are saying here. Instead of plus, we are saying a multiply, but this is only true if I get a positive, if I is a positive number, if nums I is positive. Right? Others? Is this good so far? I have not taken the case of the negative, but other than that, is this good? So now let's take the case that I is negative. Now, if I is negative, can you say that whatever maximum product subarray I get ending at I minus 1, I can multiply that to I and I can get a maximum product subarray ending at I of length more than 1? Can you say that? You cannot say that, right? Because if this product is 3, you would, and you have a minus 2 here, you would say this, the maximum product subarray ending at this is minus 6. But actually, you could have a subarray ending at I minus 1 whose product is minus 2 also, right? So then minus 2 into minus 2, 4 will be greater than 3 into minus 2, right? So from here I am concluding that, but what if I take the minimum product subarray ending at I minus 1? So whatever is the smallest product subarray ending at I minus 1, if I multiply that to this, then I will get the maximum product subarray ending at I of length greater than 1 for negative, right? Just think in English, don't think examples. Whatever is the minimum product subarray ending at I minus 1, I get. If I multiply that to nums of I, then I will get the maximum product subarray ending at I. If nums of I is negative, if nums of I is positive, then I will take the maximum and multiply it, right? All this is for length greater than 1. For length 1, I already have a case, which is fine, right? So from here, I conclude that for a given I need two kinds of information. Till I minus 1, I need the maximum product and I also need the minimum product. So I need the max product and I need the minimum product. So basically now I can store two values. Building from the, so this is the problem. Now, again, you can check for yourself that this has overlapping subproblems. How? When you are doing it for I plus 1, you will be needing I, you will be needing I minus 1, you would be needing I minus 2. For doing I plus 2, you would be needing I plus 1, you would be needing I again. So you have a overlapping subproblem. For I plus 2, when you are doing, you are needing I. For I plus 1, you are doing, you are needing I also, right? So you have an overlapping subproblem. So from here, you could say that let me construct the subproblems in an increasing manner, starting from the smallest subproblem. So the smallest subproblem is a prefix array of length 1, right? For this. So for this, if I compute both of them, that is min pi. So min pi denotes the maximum product subarray ending at I, and max pi for A0 to I. I mean, you could say it for the entire array also, it does not matter. Max pi is maximum product array. This is minimum. Ending at I for A0 to I. So I can then say that min p of 0, which is basically for the smallest subproblem I'm storing in the table, is equals to max p of 0 is just nums of 0, right? That will be the smallest subproblem. And now I can compute the bigger problem in this manner using this decision. So when I'm doing it for 1, I could use the decision of till 0. We will see the code, but do you understand the overall idea? Right? Everyone understands this? Can I have more acknowledgements? Yeah, Darshan. You have a question, Darshan? Okay, cool. So let's code this then. So get a feeling for the subproblems also. So I said that my actual problem is reducing to the task of finding for all the, so I will keep two arrays. One is min p, as I said, for n, and we will keep the max p for n. Now what I'll do is I will, for the smallest subproblem, So for the smallest subproblem, min p of 0.
Sir, can't we take pairs?
Yeah, you can take pairs also. Nums of 0. Now I will start from 1. Now I have 2 cases. So whatever cases I have, can I always write this, that max pi? Just see what I'm writing. It is the max of whatever you get from nums of I and max of or let's store it in a temporary variable. Max of nums I max of nums I into max p of I, nums I into min p of I. So whatever that is, I can put it here. This will take care of the sign also.
So max p of I minus 1.
What?
Max p of I minus 1.
Yeah, I minus 1. Yeah. And T2 will be just, or you could reuse T1 again. Who cares? So it will be the min of these two. You can actually use if else's also. The logic that I said, wherein you are if checking the sign, but that is being encapsulated in this. T1. Right? And your result is you could start with 0. Or your result you could start with int min because it contains at least one number. You could just say initialize it with 0. This is just the running result. You could do it in a second pass also. It is the same. And you could return the result from here.
Sir, why you are giving same name for T1 for max and min?
You can use another name. I have just reused the same variable.
Okay.
I mean, once I have done with this value, I am not using this anymore, right? So I'm just reassigning it another value. You could use T1, T2 for more readability. Or you can just put it here also in the expression itself.
Okay.
And I'm taking the maximum because it could end at any of these indices. So that's basically the logic. Clear? Is it clear? Crystal clear? You get an intuition also for all these sub-problems. So I've given you 2 types of sub-problems so far. I've given you 2 types of decisions and 1 sub-problem, like 2 types of sub-problems, prefix arrays and suffix arrays, and 2 types of decisions. One was include, exclude, and one was the maximum including I. Right? So I have done that much so far. So if any part is not clear, let me know. Whatever I have taught so far assumes that you know some part of DP. So we have not really like gone very basic. So if somebody wants that, then let me know that also. Now let's do another question. This will also be quite interesting.
Sir, by taking that min pi, are we like considering if all the i's are negative or only one?
Come again.
Sir, by considering by taking min of pi, are we going to consider for all the elements of I or the single element, assuming it as negative?
We are taking whether num psi is negative or not. See, if num psi is negative, then out of these two products, which will be the more? Which will be more? This will be more, right? If num psi is positive, then this will be more.
Yeah, okay.
So I have just taken care of that in this max. You could use if else also. Right, Karan? Did you understand this? I have just encapsulated that in this. I have said always take the max of both. Either multiply it with minimum or multiply it with maximum. Take the maximum. You could use if else. I'm not saying you cannot, but you could do that. If num psi is positive, then take this. If num psi is negative, then take this. That would be for max. For min also you would have to do that. If num psi is negative, then take this. If num psi is positive, then take this. Right? And take. So you could do that. I have just encapsulated both of them in this max. So now try 978, this question. How can you do this? This is actually simpler than the product question. First thinking is the same, right? The result will either be a subarray ending at I, ending at 0, ending at 1, ending at 2, or so on till n minus 1. So I will find for any I will find the length of longest turbulent subarray ending at I. And then I will take max across all these i's to find the length of the longest turbulent subarray for this array. That is the first line. Then the second level of thinking is now I have to find the length of longest turbulent subarray ending at I. Right? So when I am about to find the length of longest turbulent subarray ending at I will again use the same decision that I told you to either that subarray will be of length 1 or it will be of length more than 1. Right? So if it is of length 1, you will only have AI. Correct? But if it is of length more than 1, then you want the longest turbulent subarray ending at I minus 1. You have to extend that somehow. Right? So when can you extend that? You have two cases here, right? If AI is greater than AI minus 1, then you have to extend the turbulent subarray ending at I minus 1, which just decreased at that I minus 1. You can only extend that. You cannot extend the turbulent subarray ending at I minus 1, which increased at I minus 1. Correct? Do you get this? So how do you do that then? Like how do you assemble all these thoughts? Any ideas? Is everyone blank?
So we can make two cases. Suppose we do for the case 1 when AK is greater than AK1 when K is odd. Right. We can have two types of turbulence surveys now. So suppose we are solving for the first one. If we are solving for the first one, then we can form any subarray ending at I. If it is ending at I and I is odd, then we will see for I minus 1 what is the longest subarray. And we satisfy, and we check if we can satisfy the condition which is given in the question, that if it is odd, then it must be greater than I plus 1.
Yeah, it is basically what you are saying. I got your thinking. I'm not able to describe it, but I got your idea. So basically, we want to find the longest turbulent subarray ending at I, right? That is the problem that we want to solve. Till here, everyone is fine, right? How our eventual result will be max across all these I's. Now, for finding the longest turbulent subarray ending at I, what we are saying is you have two cases. If you want to get a length 1, then it's just nums of I. Nums of I. If it is more than 1, then you have two cases here. If your nums, you have to extend any turbulent subarray ending at I minus 1, right? If you want a subarray of length more than 1. So you have two cases. If nums of I is greater than nums of I minus 1, then what does that mean? That means that whatever the longest turbulent subarray that you got till I minus 1, which was of this type, at I minus 1, if it decreased, you have to extend that and include the I, right? So you have to, let's call this as TS1. So then you will have TS1 plus nums of I. Otherwise, if nums of I is less than nums of I minus 1, what does that mean? That this is I minus 1 and this is I. You have to then find the longest turbulent subarray ending at I minus 1, which increased at I minus 1, right? And extend that. So call this TS2. So you will, this will be TS2 plus nums of I. And you will take the maximum of all these.
Sir, instead of taking two different TS, we can also store a pair in DP, and which will denote the maximum as well as the parity of the maximum element, the parity of the.
That will not help. That will not be enough, right?
Not the parity, sir, whether it was decreasing or increasing.
I got that, but that is not enough, right?
Why,
so
sir?
Why? Because if you have till I minus 1, let's say you had this case, that this was the maximum. Okay.
Yes, sir.
Now I, if you get such that A of I is greater than, or nums of I is greater than nums of I minus 1.
Sir, in the pair, sir, in the pair we can denote signs, whether like if the number is ending at a greater note, then we can store 1. If it is ending at a lesser note, then we can store minus 1.
You will still have two arrays, right? You will still, basically the size is 2n only, right?
Yeah, it will be a pair basically.
That is okay. That's the implementation, right? That's okay.
Yeah.
That's not very like crucial also. It does not matter. The space is 2n, right? You could use a pair or you could use two separate arrays. That I have not talked about. But what I am telling you is till I minus 1, you need two kinds of information to solve for I.
Yes, sir.
Which is, one is that if it decreased at I minus 1, whatever is the length of longest turbulent subarray, and you need the length of longest turbulent subarray such that it increased at I minus 1. You need both this information, and depending on this case, you would use one of these. Correct?
Sir, why we are worried about I minus 1 is increasing or decreasing after that?
We are not worried about I minus 1 is increasing or we want to make the array turbulent at I. So we consider two cases. Either the last edge that you add to the turbulent array, either it will be like this or it will be like this. If it is like this, then you cannot extend a turbulent subarray which is like this. You cannot if like this at I-1, you cannot extend it to make it I, right? So even though the absolute turbulent subarray ending at I-1 might be of this type, but you cannot extend that to make it for I, right? Because I is less than I-1. Nums of I is less than nums of I-1. So you have to keep both the maximums. Did that make sense?
What is meant by we have to keep both the maximums?
So we have to keep two turbulent subarrays. One is the turbulent subarray such that the last edge is this type, and a turbulent subarray ending at I such that the last edge is this type.
Okay, okay.
वो सेम चीज लिखा हुआ है, वो यही लिखा हुआ है बेसिकली. जो वो लिखा है वो मैंने फोटो में बनाया है. So इस ठीक है. How many of you have questions? Pradyum, is it clear or should I explain mathematically also? Others? So the same thing basically, it is like the product only. Yeah, Ayanva, are you understanding things? Divya, long time no acknowledgement. Dominic, Hemant, you have not acted since the last week. Pranav, what about you? I think Pranav acknowledges. तुषार, आज तो आपने बोला ही नहीं है, पता नहीं क्या हो गया आपको. ठीक है. So then just the same question, same approach we will use here. We will have two arrays. One will be, let's call it INC. So INCT. So increasing turbulence. So that means that the last edge was an increasing edge. So last edge had a positive slope. Let's just say that. And let's call another one the decreasing turbulence. Let's of size n. So what is the smallest sub problem? So what is the length that's given? Length could be from 1. So the smallest problem is of 1 length, right? So for 1 length, INCT 0 will be equal to D decreasing 0 will be equal to A of 0. And now I can go from 1 to n.
So A of 0 to 1 sir.
That is?
Sir, A0 to value होगी ना, हमें तो length store करना है.
अच्छा, length. Thank you. 1 होगा वो. So now you have two cases. If AI, so you have to update both of them, right? So you can simply, so now see, if AI is greater than AI minus 1, then what does that mean? That means ki INCTI will be 1 plus DECTI minus 1. Whatever I got such that the last line was decreasing, I added 1 to that. And what will be DECTI? That will be 1, just this number. And the other cases, I will use the same thing, but the other way. So if it is, if AI is less than AI minus 1, then DECTI will be basically 1 plus INCT I minus 1, and INCT I will be 1. That's it. And I will have a result which will be int min, let's say, and you have 1 here. You can just keep taking the maximum of both of them, right? So it could increase at I or it could decrease at I. Where did I scroll? Yes, the equality part is where I screwed up. So you will have 3 cases. That if AI is, so this will be the same thing but decreasing. And finally, for the equal case, I will have both of them as 1. You could make this code cleaner. For equality case, it will be 1, right? So you can actually make this cleaner in this way. If this is there, then make this. If this is there, then make this. Remove all this bullshit. This will also be fine.
Sir, could you repeat that? What is in line number 16? Why we 1 plus? What is that 1 plus?
See the same, see this code, don't see this. See this code. Yeah, now tell me. Where, which line number?
Yeah, in 15 and in 19.
Yeah, so it's the same thing. Basically, see, if the current number is greater than the previous number, then I can extend the chain I can extend the chain which decreased at I minus 1 by 1. And that will be the longest such that it increases at I. Correct? And in this case, because the previous number is smaller, I cannot have a turbulent chain such that it decreased at I and ends at I. I cannot have any chain, right? So I will have just this number. Does this make sense, or should I show it?
Sir, on whiteboard. Could you show?
Yeah, I will show it. Don't worry. See, 2 cases I have. I have I minus 1 and I have I. So I could be either greater than I minus 1 or it could be less than I minus 1, right? So now think about the case when I is greater than I minus 1. When this is the case, what will be the length of the longest turbulent chain ending at I such that the last edge is like this? What will that be? That will be the longest turbulent chain ending at I minus 1 of this type, and you extend it by 1. So this was DECT I minus 1. decreasing T. So decreasing turbulence at I minus 1. So that means that the last stage was decreasing. That's the notation that I've used. You could use better name. So INC, and this is INCTI. Increasing at I. It will be 1 plus whatever I got. And what will be the longest turbulent chain ending at I such that it decreased from I minus 1 to I? For this case, you will not have anything, right? Because this is inherently I is greater than I minus 1. So you cannot have any chain which ends at I and decreases from I minus 1 to I, right? So that's why for this case, I said INCTI is this plus 1 and DECTI is just 1, which is this element itself. And the same analogous case for this. When I is less than I minus 1, I can only extend this kind of a chain, which increased at I minus 1.
Okay. What?
Did you get it really, or should I can explain it again if you didn't get it?
Yeah, yes.
You got it, right? Others? Does this code make sense? Cool. So let's do one more question of this type. That's a slightly more involved one. Okay, you want to do this? Let's do this. This is 32. So give it a try, 32. This is a good question actually. So you have to find the longest valid parent. I'll give you a hint. Ending in this. Yeah, I mean, think more. So you have to find the longest valid parenthesis substring in a string. So whatever that will be, it will end at some index, right? So what I can find for all i's, the longest valid parenthesis string ending at that index. And I can take the maximum of all. That's the first line, which is similar to what we have been doing for all the questions so far. Now you have to basically, now the problem is for 0 to I, you have to find the longest valid parenthesis substring ending at I, right? So what are the cases here? You have two cases. If A of I is an opening parenthesis, then the longest valid substring parenthesis ending at I will be 0, right? Because this is not a valid, any parenthesis expression that you take ending at I, it will not be a valid parenthesis because you have an opening parenthesis, right? You understand this case? What is the other case? The other case is what you have to figure out as homework. If AI is a closing parenthesis, then you need to write some expression here in terms of previous i's. And that expression is hard. That's why this question is hard. But it's not very hard. Okay, so give it a try and consolidate all the ideas that I gave today. So I'll just summarize what we did today. So we in short looked at two types of decisions. We looked at a decision called include exclude, and we looked at a couple of problems of house robbers in that, and we 1 and 2. So in this we looked at when we were doing this decision, the eventual sub problem that we were left with was a prefix or a suffix subarray. And we looked at another type of decision, which was the decision of longest valid something ending at that particular index. If that is the decision, if that is the sub problem, then my decision was that either of right. And for this, I said that you have a prefix or again you get a prefix or a suffix subarray. That was the sub problem, and all these sub problems that you were able to compute in O1 time, right? So any DP of I you were able to compute in O1 time. So that's why you just had to populate from DP of 0 to DP of n or n minus 1 and get the answer. Tomorrow we will look at, to begin with, we will again look at 1D sub problems, but the overall complexity of solution will be n square. So computing this DP of I itself will take order of I time and will not be an order 1 time. So you will have to iterate over all i's less than I to compute DP of I. So in that way, the total complexity of the problem will be, solution will be n square, but the sub problem will still be a prefix or a suffix array. So we will look at that type of sub problem first and what kind of decisions involve them. And then we will gradually increase the complexity. We will look at 1D sub problems again, which have an n cube complexity. And finally, then we will start with 2D sub problems. And in 2D sub problems, we will have all kinds of fillings we have. You can fill a 2D sub problem row wise. That is one thing we will do. And you could fill it lengthwise. So we will look at those types of sub problems where you can fill it lengthwise. And so 2D sub problems in n square time we will look at, and then we will look at 2D sub problems in n cube time. So you need another n time for something. So that is what we will look at tomorrow. And then we will look at matrix DPs also after that. But this is what we did today. I gave you one homework, valid parenthesis, just try that. It's not very hard. Like it's not as hard as some other hard questions on LeetCode. Okay? So everyone, can I have one final acknowledgement that you understood everything that we did today? Whoever was there in the class, like now I want from everyone, not just 5-6 people. Like you got a proper feeling, right? Intuition as to what you are doing here. The intuition is more important. With others, more acknowledgements. Sanyukta, Sushrit, Utsav. Yes, to chala gaya.
Sir, here subarray wala big O of 1 time. Like for computing subarray, we have big O of 1 time. Is it? And what when we combine all?
For computing one particular prefix subarray, we are using constant time, right? We are just using I minus 1 or I minus 2, just one value we are using. Okay. So it's a constant time operation, but we are doing it for all the i's, right? So that is taking n time, and that's how the total complexity is n. This is the simplest type of DP problem that you can get. 1D sub problem, order n time. Yeah, Karan. Okay, I will just share it. I'll tell Gaurav to share it. If I forget by today, do You can just ping me and remind me, okay, just once. But mostly I will do it. Okay, I just forgot yesterday. That was my mistake. If AI is an opening parenthesis, then the expression will be longest subarray. If AI is opening parenthesis, then it will be 0. That's for sure. If AI is a closing, then the expression will be longest subarray ending I-1. हाँ, तो इसको formulate it in terms of the original problem. Your sub problem in English should be the same as the original problem, right? The original problem, you just have the longest subarray ending at I, longest sub valid parenthesis substring ending at I. We just have that. हाँ, DP with bit masking भी करेंगे. So look at that I-1 in that scope. It's actually easy. See, if you have a closing parenthesis here, what you have to do is you have to match this with a corresponding opening parenthesis, right? Where will you get that match? That will be the longest, whatever is the longest valid parenthesis at I-1. Just one left of that, you could find the matching. है ना? तो अब सोच के देखो, अब अभी भी नहीं हुआ, इतना समय भी नहीं होगा. अगर so you could match it. So if this is again closing, then for this you will get a 0, क्योंकि आपने इसको मैच नहीं कर पाया. ठीक है. बट अगर ये ओपनिंग है तो it will be 2 plus this. But will that be all? It will not be all. अब आप सोचना कि why is it not all? There will be one more term which will come here. वो एक्चुअली इजी है फिगर आउट करना, वन मोर टर्म कहाँ से आएगा. ठीक है. ऑल राइट गाइस, देन लेट्स टॉक टुमारो अगेन. इफ यू हैव एनी क्वेश्चंस आई विल स्टे अराउंड फॉर अ कपल ऑफ मिनट्स.
सर वो वन मोर टर्म हो सकता है ना कि ये वाला जो क्लोजिंग ब्रैकेट आपने लिया उसके पहले भी एक हो सकता है.
हाँ वही होगा एक्चुअली. So it will be this part. इसका जो लेंथ है वो यहाँ आएगा. So this will be the total answer. मतलब इस वाले यहाँ पर एंड करने वाला जो मैक्सिमम वैलिड सबस्ट्रिंग है, पैरेंथेसिस है, उसका जो लेंथ है वो होगा वो वाला. तब ये पूरा का पूरा टोटल एक वैलिड बनेगा. Right? Anyone else understood this? We will discuss it exhaustively like tomorrow, but किसी को समझ आया तो अच्छी बात है. Yeah, this implementation will be, क्योंकि ये सब out of bound जा सकता है. They can go less than 0. So that's the challenge.
तो उससे अच्छा हम लोग ये इनवेरिएंट भी मेंटेन कर सकते हैं ना कि longest subarray such that the number of opening brackets is one more than number of closing brackets. ये भी मेंटेन कर लेंगे.
ठीक है.
एक और एरे में तो फिर अगर क्लोजिंग ब्रैकेट आता है तो उसका लेंथ देख के उसमें 1 ऐड करके स्टोर कर देंगे.
ठीक है. और ओपनिंग आया तो
ओपनिंग आया तो जो फिर 0 वाला निकालना पड़ेगा. फिर 0 वाला निकाल के उसमें 1 ऐड करके दूसरे वाले में स्टोर कर देंगे जो जिसमें 1 ज्यादा अपन स्टोर कर रहे हैं उसमें.
फिर 1 वाले से 0 में कैसे जाओगे? 0 और 1 दोनों कैलकुलेट करके रखोगे आप बेसिकली ना.
हाँ दोनों.
तो 0 और 1 दोनों को अपडेट करना पड़ेगा आई पे डिपेंडिंग ऑन. तो 4 केसेस होंगे
जैसे हमने टर्बुलेंट वाले में किया था, सेम टाइप का कुछ.
हाँ मतलब work it out. If it works then it is fine. Yeah, I mean it makes sense at a very high level, but yeah, we'll see. You can think more on that. All right, guys. Then I will see you guys tomorrow again with more problems. परसों तक तो बहुत टफ हो जाएगा डीपी, तो make sure you for like revise, because abhi you are able to visualize sub problems because they are 1D sub problems. 2D maybe you will be able to visualize, and then we will move on to higher dimensional 3D sub problems also. So 3D sub problems mein to you will not be able to visualize also, so it will all be like सिर्फ माता रानी की कृपा से होगा वो, तो make sure you follow. Yeah, I will do. Can you send? So on this 1D DPU, are you talking? So 1D DP order n, that is pretty much like the type of problems that you get. 1D DP order n square is really the thing that is asked mostly. So 1D DP n square, when we do, I will send those questions which we will do. Okay, 1D DP ON is roughly this at a very high level, but I will try to look up more questions. Okay, I cannot promise, but I will try and see if there are. Mostly the questions become 2D or 1D DP n square or 2D DP n square or 2D DP n cube. Those, for those types of problems, I have an exhaustive list, so I can share with you that. But I will try. I will see if there are more questions. But Hacker Earth pe hai. We'll see. We'll see. I'll share with you if there are more. 1D DP ON. Okay, guys. Thank you then. Thank you for joining. Stay safe. Stay indoors, if at all you are staying indoors. And I will see you tomorrow. I will end the meeting now. Good night.